Test. Test 1, 2. Okay, uh, let's continue with the discussion about directories. We said that linking is this, and we will talk about the difference between hard link and symbolic path. But keep in mind the difference. Keep in mind the difference between these two files. It says bad network quality again. Okay, it's gone. So I have two linked files here. One of them is a hard link. Linked as is a hard link. Linked as soft is a soft link or a symbolic link. And their file sizes are different. Remember, in the upper directory, the hard links, the file sizes were the same. So that's an important thing to remember, and we are going to see why this is happening in a few minutes. Okay, so the attendance is ready. Just fill out the attendance sheet. So let's go back again as designers of the operating system file systems. Let's talk about the implementations of these file systems. Okay, as users, as I said before, we are interested in how files are named and what operations are allowed on them and what directory trees look like. Okay, this is what I am interested in as users. But for implementers, for designers, okay, I am interested in how do I store my files and directories on the disks and how the disk space is managed and how everything works efficiently, reliably. I am paying attention to protection between the users, sharing, and etc. So these are my concerns, and we will start talking about the second part more often now. We looked at what we are doing with the files and directories before. Now I am going to look at how we are doing these. Okay. So file system implementation. Let's look at the main structure of a disk first. Okay. I am talking about the disk, but these are applicable to all kinds of storage media. Okay. Let's say this is our disk. It's a circular structure, as you know, and my information is written on the disk on tracks. Okay, these are my tracks. I am sorry for my drawing, but this is the best I can do. Okay, these are my tracks. And on my tracks, there are sectors. Okay, so this part that I have marked as a sector. So the tracks are divided into sectors. So the tracks are concentric rings on my desk, and all the information are written and read from these tracks. And tracks are separated into smaller logical units called sectors, or their physical units too. So sector 0 of a disk is important. Okay. Sector 0 of the disk is called master boot record. Master boot record. and it is used to boot the computer. When you turn on your computer, it reads this sector 0, okay? It reads this sector 0, and it executes whatever it has on that sector 0. So it becomes your first kind of operating system after the BIOS is run, okay? When the computer is booted, BIOS first reads and executes the master boot record, sector number 0. At the end of this sector number 0, master boot record, okay, there is a, okay, this is your entire disk. Okay, this is your whole disk. This picture, bad network quality, let me wait. Okay. So if I see bad network quality mark, I will stop talking. After it is gone, I will start talking. Then maybe that will solve our problem. So this is our whole disk. I am marking it with green. Okay, this is our whole disk. At the beginning, I have sector number 0. The computer reads this master boot record. Okay, whatever it has written on it, it starts executing it. So it becomes our first part of the operating system. Then after that, I have partitions on my disk. See, this disk has 1, 2, 3, 4 partitions. Each partition is a different file system. Remember the file systems? We said that as examples of the file system, I have FAT16, FAT32, and I have, let's say, NTFS, right? Or EXT. These are the file systems, okay? Windows has its own file system, Unix has its own file system, and etc. Each partition could have its own file system, okay? File system means that it specifies how you keep your files, how you keep your available blocks, how you keep your directories, and all that kind of stuff. And we will talk about the file systems in more detail. So you have your master boot record and your disk partitions. And just after the master boot record, you have your partition table. This partition table tells the operating system how many partitions are available on this disk, and it tells about the types of the partitions, whether it's an NTFS or the EXT file system. Of course, it gives the addresses of the beginning of the partition, its sizes, and etc. So this is your general file system layout on a typical disk. Okay, and if I look at the bad network quality again, I'm waiting. Okay, it is gone. So if I look at one of the disk partitions, okay, the structure changes from file system to file system, but at the beginning I have this boot block. This one includes the real operating system, okay? So BIOS first reads the MBR. After the MBR, I have the partition table, okay? After I have the partition table, and inside the partition table, I have the information about the partitions, and one of the partitions is the active partition, okay? Partition table says that, okay, this is my active partition. Okay, wait. Bad network quality. Okay, partition table also says that this is my active partition. That means that you are going to boot from this partition. At the beginning of that partition, I have my boot block. I read this boot block, and that becomes my operating system, core of the operating system, core of the operating system. Okay, so this how you boot your computer. So we are both talking about the file system and how you boot your computer at the same time, but this is kind of developed at the same time. They go in together. So after the boot block, I have my super block. Super block includes for super block includes all the necessary information about the file system, such as the buffer spaces, how I keep my blocks, and etc. free space and etc. I think I have a question. Barish asked a question. For two operating system in one machine, partition table is accessible for both. I think it's a comment, it's not a question. For two operating system in one machine, partition table is accessible for both. Barish, is that a question? Yes, it is possible. You may have more than one disk partition, of course, as in this case. This partition, the boot block might include a Windows operating system. Okay, that says Windows, and this could be Unix. No problem. And depending on the capabilities of your operating system, all of the partitions might be available to the others. No problem about the grammar. I did not understand. Is that a question or comment? But I think it's a question. Can I access the other partitions from one operating system? Yeah. Well, let's say if this is Windows, okay, if this is a Unix partition and Unix file system, okay, if I have the drivers, file system drivers for that Unix file system, yes, the access is possible. Of course, all the permissions has to be given from the partition table. Okay, so each one is a different file system, such as FAT32 or NTFS or ext. And from Windows, I can have access to ext if I have the drivers of ext for my Windows. Sometimes this does not happen. Sometimes Windows doesn't have the drivers for the newer Unix file systems. Sometimes it's just the opposite. Linux doesn't have the file system drivers for the other types of operating system. So what you are saying is not always possible. It depends. But most of the time, our modern operating systems can see the file systems of the other operating systems. Of course, you cannot run the two operating systems on the same computer at the same time if you are not using virtualization. Okay, let's go back to previous slide before. So I think I talked about everything. Sector 0 is a master boot record at the end of the MBR partition table. This table tells me starting and ending addressing of each partition. One of the partitions is active partition, and MBR master boot record. After that, it goes to that active partition and it boots the computer. The first thing MBR does is locate the active partition, read this first block, okay, boot block, and execute it. So this boot block, okay, so boot block is the real block that starts execution of your operating system. Okay, super block contains all the key parameters about the file system and is read into memory when the computer is booted. Okay, so super block contains all the necessary information. Sometimes super blocks are large, sometimes small, but they hold the key information about the file systems. So this is the super block. And the rest depends on the file system. For example, it looks like this is an Unix file system because it uses the inodes, index nodes. Okay, index nodes is used by the Unix. So it's a Unix file system. This inode stuff does not exist in FAT32 or FAT16. Okay, it's a Unix thing. So the rest of the partition changes from file system to file system. I have another question from Göktuğ. In Linux, I can access Windows files, but in Windows, I cannot access Linux. Isn't that a bad thing? Why Windows allows this in my... Well, as I said, Göktuğ, it is not, I mean, no, both ways is possible. I mean, sometimes some operating system says that my partition is mine only. Nobody is going to have access to it, because they are worried that if they are accessed directly from outside, they may be corrupted or something. Okay? So that might be the reason, but there is no technical reason that I cannot access one file system from other files, one partition from the other partitions. Some partitions are sensitive, okay? They should not be accessed by all the other operating systems. So I talked about the super block. So we know about how the computers are booted, the sequence of loading the data, and how the different file systems can exist together on the same disk. So now it is time to look at the even more detail. Okay, let's look at how the files are stored on the disk. Okay, let's go back to this picture again. Okay, so we are in a disk partition. We know our file system. Okay, I like to look at this part, files and directories, how they are stored on my system, on my disk. Remember, my disk is organized by the blocks, and I need to organize these blocks so that I can keep my files and directories on them, and we are gonna see this structure now. Okay, the first way of putting your files on your disk is contiguous layout. Okay, let's look at this picture. Let's say this is like contiguous memory configuration. Remember that contiguous memory configuration? Let's say I have 1, 2, 3, 4, 5, 6, 7 files, and let's say each one has their own blocks. Let's say each block is 4 kilobytes. So file A is 16 kilobytes. It occupies 16 kilobytes of space on my disk. And since I contiguously place my files on my disk, this would be the picture in part A. Okay, so I put part A, file A, then file B, then C, then D, E, F, and G. Okay, this is how I do that. The problem is, remember, we tried to do this before, but the problem was this. Let's say I have erased this file F with 6 blocks, and then I have erased this file, then I have erased this file D, 5 blocks. Okay, let's say I have a new file that needs 10 blocks. I cannot fit these 10 blocks into these free spaces, because although I have 11 blocks available, okay, I have 11 blocks available, it is fragmented. That's why contiguous layout, although it has some very nice properties, some advantages, fragmentation is the most serious problem. So what is the solution for fragmentation? As we did before with the memory, we do compaction, right? What is compaction? Compaction is copying files from this location to this location, etc. So you are moving your files around on your desk so that you don't have these kind of fragmented disk spaces. Okay, so fragmentation is the biggest problem for the contiguous layout. Contiguous layout. Good. So you might think that compaction is a problem. I mean, it will take. Remember, I mean, dealing with the disk takes time. It is so slow. So I cannot deal with the compaction. You might think that contiguous layout is not used at all for the file systems. No, it is not true. There are very nice cases, perfect cases for contiguous layout, and it is commonly used, as we will see in a few minutes. So advantage is simple. So, okay, to represent a file, all you need is, okay, for that file, you say that, let's say this is my directory. Okay, this is my directory. All you say is your file name, your starting address, and your size. So bad network quality, I will repeat it. So all you need is your file name for each file, your starting address, that's the starting block number, and the size. Okay. I'm still waiting for this bad network quality to go away. Yeah. So the file name, starting address, let's say 0, and size is 10 blocks. Okay. Another file name to start 25 blocks. So it is so simple. Starting block number and the length. Once you have this information, you go to the starting block and read a sequential, make a sequential read operation. So it is very fast to access your files, and sequential reading is very, very fast. But the problem is with the external fragmentation. That means that if you do this, after you remove some files, you will end up having holes in your disk structure, and you need to run compaction from time to time. Also, appending is a problem. Appending is problem. Let's say if you like to add one more block to this file B to make it 4 blocks. Okay, so how are you gonna do that? Either you are gonna remove file B from that location, or you're gonna push file C 1 block over. That's a problem with this kind of contiguous layout. Ali Haidar has a question. This have thousands of gigabytes, and they are not as expensive as main memory. So why do we care about external fragmentation? Well, I mean, even I mean, what is the rule about the memory and the CPU? Doesn't matter how large your memory is, how large your disk is, you will end up using all of your disk. Okay, you will end up using all of your disk, and external fragmentation becomes a very serious problem. You may end up not using half of your blocks available. After a while, okay, you keep deleting and creating and deleting and creating new files and old files and etc. You may end up very, very fragmented disks. You may end up not using half of your available disk space. That's a serious problem. 5% bad network quality. Wait. Okay. 5% fragmentation is not a problem, maybe. It is manageable, but 50%, 60% fragmentation makes it very, very inefficient. I mean, I paid $100 for a 1 terabyte disk, and I'm not using half of it. If I pay, let's say, $20 for a 500 gigabyte disk, and if I don't have any fragmentation, then I am saving $80, right? So the difference is, for large corporations, it makes lots of sense. So we don't like fragmentation. We don't like fragmentation. We need to eliminate it. We need to deal with it. Okay. So, but for some cases, fragmentation is not a problem. What is that case? As we said in the previous slide, the case is this. Let me put it in here. The case is this. Contiguous allocation is feasible if I am writing my disk on CD-ROM, okay? Because CD-ROMs are read-only memory, right? You don't delete files from your CDs. You just write them. So contiguous allocation is possible for the CD-ROMs, and there is no risk of external fragmentation, because the only reason why I am having external fragmentation is deleting files or appending files. In CD-ROMs, you are not allowed to do that. So anyway, all the advantages are there, okay? And all the disadvantages are not valid for the CD-ROMs because there is no file deletion or appending. Okay, so contiguous layout is one thing. So, by the way, this is our first example. This is our first example for a file system. Okay, contiguous layout file system. It's very simple. How do you keep your files? Like this, as a table. For each file, you have your file name, all the file attributes, and you keep the starting address, block address, and the size of the blocks in your directories, and that becomes your contiguous layout file system. And CD-ROMs are done that way. And let me try to find the exact name for the CD-ROM file system. CDRFS. Okay. It comes from IBM. I guess it would be reliable, maybe. I think they okay. As you see, the CD-ROM file system is a read-only file system. CD-ROM media. But it says that it could be used for read-write media too. Oh, okay. So this is the standard file system I saw in 96, 1960. CDRFS. Okay, let's see if this one is read-only. CDFS. So CDFS uses contiguous allocation of the files, and there is no problem. Okay, there are three levels of this file system. Okay, file names are limited to 8 characters, very old file system. 3-character example, also file systems. Directory names are limited. Files may contain one single file section. Okay, you cannot divide your files into more than. So this is a typical contiguous allocation system. And in level 2, again, it's contiguous, but the file names could be larger, etc. So read about this your literature. So this CDFS uses this idea, and this is a simple CDFS type file system. Okay, good. So what if I am not using bad network? What if I am not using CD-ROMs? Let's say I'm using a regular disk. So fragmentation, either I will do this compaction from time to time, or or I need to find some kind of other solution. Okay, some kind of other solution. The solution is linked file allocation. Okay, you don't keep your files as contiguous locations. You divide them into different parts, and you keep your blocks as linked lists. Okay, this is the idea. Let's say file A has 5 blocks. Okay, file A has 5 blocks, and the first block is this one, 4 kilobytes of data. After that, there is a link to second block, and the third block, fourth block, and fifth block, etc. It goes that way. And these are my block numbers. Okay. So reds are my block numbers. Blues are my logical file block numbers. Okay. So with this one, there is no problem of finding contiguous space for a file. I can put my files, I divide them into blocks. Of course, I have to do that. I can put my files in any place as I like, because I don't have to keep them contiguously. Linked list allocation. Okay, this is called linked list allocation. Okay, let me wait for a minute, for a few seconds. Okay, so, and this is my second file, B, linked list allocation. This solves all the external fragmentation. Internal fragmentation, we did not solve it, right? External fragmentation, we solved it, but the internal fragmentation is there. What is the internal fragmentation again? Somebody tell me the internal fragmentation. What is the internal fragmentation for a file system? What is the internal fragmentation?
It happens when the inner data of the file is modified.
It happens, say it again, Yasir.
When we delete blocks from the file, inside of the file, but the rest of the file remains. So we have an empty space in the middle of that file.
Well, it is difficult to have space in the middle of the file. But let's say, what did we say for the file A? What is the size for file A? File A has 5 times 4 kilobytes, right? It is 20 kilobytes. If I have perfect 20 kilobytes for A, it is no problem. But if I have, let's say, 17 kilobytes, that means that the 3 kilobytes of last block will be wasted, right? And the same thing again here. This is for file B, 12 kilobytes, no problem. But let's say I have 9 kilobytes. If I have 9 kilobytes, then again, the 3 kilobytes of the last block will be wasted. This is called internal fragmentation. And internal fragmentation is a problem for both contiguous allocation and the linked list allocation. So there is no solution for the what is the perfect solution for internal fragmentation? Just tell me the perfect solution for the internal fragmentation. Well, it might not be a good solution for many other cases, but for the internal fragmentation, there is a perfect solution. Small block size, exactly. How small? 1 byte. If you make your block size 1 byte only, there is no internal fragmentation. But it's a very bad way of solving things, because if you make your block like 1 byte, that means that you will have a linked list of file structures, and each node is a single byte. You are wasting lots of space, because those links will occupy more space than your file information, right? So keeping your block size small is not a good idea. It should be balanced. Okay, so let's go back to this linked file allocation. Each file is a link of disk blocks, and each block contains an X pointer, and directory only needs to store the pointer and the first block, and blocks may be scattered everywhere on the disk. So our file system could look like this, right? Like this. My file name, f name, and then my start block number. I don't keep the size, right? Because this is like a linked list. You just give the header of the links, and that's it, linked list. So advantage is space efficient, no external fragmentation. Appending is so easy, right? You go to end of the file and that's it. But the problem is the random access, right? I cannot go to the, let's say my file A has 2000 blocks, and I like to go to block number 1507. So how am I going to do that? If I like to access the kth block, all I need to do is go to the beginning of the file, okay, read each block one by one and follow the links. That's very slow. So random access is slow. For the previous case, random access was very good. Why? Because I don't keep them in separate places. Since I know the beginning of the file, then I know the beginning of the file. All I need to do is go to that beginning of the file and just make a multiplication. So Ahmet has a question, Yasir has a question. Why don't we keep the file size in the table? Sure, yeah, I mean, you could use it, but usually, you see this? The place that I'm marking with red, there is no next pointer, right? With the linked list, we don't keep the size. Well, in the file attributes, you have it, of course. You have the size of the file in the file attributes, but you don't have to store it in your file representation table. Okay, so, but the book says the poor access speed. Why do you think the sequential access is slow? It says that random access is slow. I told you why. Because to be able to reach the let's say kth block, you need to follow all the links. That's why it is slow. But it also says that the sequential access is slow too. Can anybody tell me why? For the previous case, for the contiguous allocation, both random access and sequential access was fast. We said that, right? I understand why the random access is slow for linked file allocation, but I don't understand why it is slow for sequential. Can anybody tell me why it is slow for the sequential? It has something to do with the it has something to do with the physical hard drive structure. As Ali Haidar said, yes, they are not on the same track. Remember our disk structure, hard disks. This is my disk, and these are my tracks. If my file has blocks like here, 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 and here, okay, and they are linked. If they are linked like that, I need to move my read-write head from track to track. Okay, I need to move my disk head from track to track, and that's expensive. That takes milliseconds. Okay, that's like computer years, right? That's very, very long time. So even the sequential access is so slow. Previously, for the contiguous allocation, everything was on the same track. I just read them one by one. Okay. Okay, so there is not much we can do about the sequential problem. All we can do is maybe you could do this. Maybe you could just be smart and do this. Put all of your blocks on try to put them on the same track and do this linking. Okay. If I can, I could do this. So keep them on the same track as much as possible. Keep them on the same track as much as possible. If I cannot, due to fragmentation, just then in that case maybe do this linking, right? So maybe I can access this sequential stuff, but for random access, again, random access is a problem. So how would you solve this random access? How would you solve this random access problem? It is, I don't understand what you are saying, because it has to go through all the files sequential. No, it doesn't have to. I mean, if I have my file name and the starting block number, that's all I need to go to that to find that file, and after that I start reading. Okay, I'm asking a question. How do you solve this random access problem? For the sequential access, I tried to give you a solution. I said that try to keep all of your blocks contiguously. If you cannot, because of the fragmentation, just make a link. So this is the best trade-off between good sequential access and the external fragmentation problem. So that's kind of solved it. At least addressed it a little bit. How about the random? How would you solve this random access problem? That would be our next file allocation technique. Keeping block size same length. That's already what we are doing, Furkan. Our block sizes are 4 kilobytes. The problem is I don't know where my 5th block is when I open my file. I have to follow all the blocks until I find the 5th block. This is exactly the same as linked lists you have seen from your data structures course. To reach a node, you need to follow all the links. That's why the access time for a node is O(n), right? For the array, it is O(1) because I know where it is. Array is contiguous, linked list is not contiguous. So how would I improve this? I'm not going to do a hashing and that kind of stuff, but all I'm saying is that the problem is bad because these are all on the disk. Okay, each block is on the disk, and reaching a block takes lots of time if the blocks are on different tracks. Okay, so making this disk operation is very costly. So the idea is let's keep this linked list structure in my memory. Okay, let's keep it in my memory. Okay, linked list, but I keep this linked list structure in my memory. Let's say on my left, okay, I have total of 16 blocks. It's a very small disk, okay, this very small partition. It's happening again. Okay, it's a very small partition. There are 16 blocks on my disk, and this is my linked list table. Okay, so my file system becomes this. Okay, this is my file name, and this is my start node. For file A, file name A, start node links that position. File B, start node links to that position. Okay, so I keep this linking information in my memory. So instead of going to the disk to find the 5th block on my file, I do all of this stuff in my memory. So it's a linked list. I need to follow the links, but following these links will be millions of times faster than following the links on the disk. Okay, so that's the solution. That's the solution. I keep this table in my memory. So what would be the disadvantage of this method? We always do this, right? We solve the problem, but we introduce another problem. So this question is, what would be the disadvantage of this method? We are going to look at it first, but I am out of time. And I will talk about the difference between symbolic linking and hard linking, because now it is time. But before that, I need to stop here. Tomorrow we will continue. I will try to find a solution to this network problem. I don't know what's happening. My network connection is good. I mean, I measured it. It is good. Okay. I'll see you tomorrow then, if there are no questions.
Hala
Okay. Okay, see you tomorrow.